So the next speaker is Brett McLean, please.
Okay, thank you. So this is just going to be like it's supposed to be a somewhat accessible introduction to just some things I work on. So there are not going to be any technical details. I might mention some words about the methods we use in the proofs. So if you're familiar with those things, then the words will be familiar. So yeah.
Maybe you can hit the button, okay?
Okay. So the three topics are particular temporal logic for space-time, intuitionistic temporal logic, and algebras of partial functions. Okay, so the first topic I've worked on directly with Robin Hirsch, and Mark Reynolds has also done some work on this subject. So since this is a bit introductory, we'll just first go over what the basic temporal logic is. So we start with propositional logic, the usual connectives that you're familiar with. And then we add these two modalities. So for any formula phi, you can form the formula f phi or the formula p phi. So f is saying that phi is true at some point in the future, and p that it's true at some point in the past. So let me spell out the semantics precisely. So we use Kripke frames, which are, of course, a set with a binary relation that's in this situation telling you which points are in the future if you look forward in the relation, or conversely, the past is looking backwards. In order to evaluate a formula, you need evaluation, which tells you which of these points in the Kripke frame the atomic propositions are true. And then you need to pick a point at which you're evaluating at. And the key point is about the modalities. So f of phi is true if at a point W, if there exists a point V that the accessibility relation tells you is in the future, where the phi formula holds. And similarly, P of phi holds at a point W if there's a point in the past where phi holds. So the tense logic of space-time is about doing this on a particular frame. And so if we want to talk about time in temporal things in space-time, Einstein's relativity tells us that depending on the inertial frame we choose, that can affect whether two particular points are considered two particular events are considered to occur simultaneously, or one is after the other, or vice versa. However, there are certain relations that are invariant under inertial under changes of coordinates to different inertial frames. So saying that one point can be reached with a light speed or slower signal is invariant under changes of coordinates, and similarly saying that you can reach a point with a slower than light speed signal. So the setup is to treat space-time as a Kripke frame, and the accessibility relation will be one of these two relations, light speed or slower than light speed. And then we'll study the logic I just mentioned on this frame. And we're just going to be dealing with flat space-time, the most simple space-time where light just moves in straight lines. So here's a picture with the light speed or slower relation. If I take a point, then the points in the future of this point here form this blue cone, including the boundary, and conversely, there's a past light cone below it. And if I say that accessibility is the slower than light speed relation, then that just means that I'm excluding the boundary. So this point cannot see these points on the boundary in this future. And of course, here there's a decision to be made about how many spatial dimensions we use. So time I'm indicating in the vertical direction, but of course we could vary the number of spatial dimensions. And just to say some introductory things about validity, formula is valid if on a particular frame, if for every valuation at any point that we choose, the formula is going to be true. So an example that is true on either of the space-time frames I mentioned is this one. We call it density. So if you think that if something P happens at some point in the future, then we can choose some intermediate point that's in the future, that's a little bit less in the future, but still in the future, where that can still see the P point. For this world here, and P holds here, so that F of P holds here, then this point can also see P, so F of P holds here, so F of P also holds here. A more interesting example, this formula we call two density, and this is valid on the slower than light frame, but not on the light speed or slower frame. So on the slower than light frame, if my point can see a P point and a Q point, then they must be strictly in the interior of this region. So I can go forwards a little bit, and then they'll still be in the interior of this region. So if F of P and F of Q holds here, then F of P and F of Q holds here. So F of P and F of Q holds here. But in the light speed or slower frame, it could be the case that these P and Q are on the boundary and on sort of different parts of the boundary. So now, if I start here, I can see both of them. But if I go forwards in time, then I'm going to have to lose contact with at least one of them. So I could choose to go up here, and then I'd lose contact with both of them. I wouldn't be able to see either of them. I can maintain having Q in my future or P in my future, one at a time, but not both at the time, both at the same time. So the validity problem is for a particular frame is given the formula, decided it's valid on the frame. And here are some results we have. So validity on the frame. So this is the frame with with the temporal dimension and one space dimension. And on both of the frames I mentioned, so the slower than light speed or the light speed and slower frame, the validity problems are P space complete with one spatial dimension. Yeah, that's what I just said. And but in higher dimensions, so if we have more than one spatial dimension, then we know that the validity problem is extra time hard. Quickly, something about the methods. So if you know about mosaic methods in modal logic, it's a sort of generalization of that. So So firstly, in one spatial dimension, this frame is exactly shown as shown here. It's just a two-dimensional thing, and the cones are just quadrants if we rotate the frame. So we viewed it in this rotated way. And then the idea of the proof is about thinking about what sort of data we could find on a small square of this space, and showing that for a given formula, there's only a finite amount of relevant things that could happen, and then you search through all of the possibilities. So that's that would be an algorithm for deciding, well, for deciding satisfiability, which is of course the complement to validity. And for the hardness result that I mentioned, is about reducing a certain extra time hard two-player game to the decision problem for validity. The game is about two players trying to tile an infinitely long corridor. So they're given these tiles that they're allowed to play, and they play, and either one of them has a winning strategy or the other one. And open problems are, so I mentioned this extra time hard, extra time lower bounds that we have, but we don't have any upper bounds for in the higher spatial dimensions. Also, we can distinguish one spatial dimension from two spatial dimensions with a formula, but we actually don't have any example of a formula that can distinguish any other, well, any dimensions higher than one spatial dimension. And we don't have any exponentializations for any of these logics yet. So we would want to add some time to validities, or have some sort of calculus for producing the validities, which we don't have. Okay, second topic is about intuitionistic linear temporal logic. I've worked on this with various authors that you see there. So linear temporal logic is a temporal logic that originates from computer science, and their time is linear and discrete. So it's just like time 1, time 2, time 3. And this is related to computer science because you're thinking about the state of the computer at each stage of a computation. So the computer has an internal clock that's ticking, and then states continually changing. So the syntax is, we have propositional logic, and then we have some different modalities than previously. We have, let's discuss these 3 modalities. So the next modality, you can imagine that's claiming that the formula is true at the next time step. Eventually means that at some point in the future, the formula is true, and henceforth means it's true now and at every point in the future. And this is useful in computer science because we can express properties that we'd like programs to have. So we might have a program and we want to check that eventually every request that comes in is serviced, or that henceforth something bad doesn't happen, particularly that the program doesn't crash. Now, intuitionistic logic is a logic that's weaker than classical logic. It's constructive in the sense that if we have a disjunction, then in a sense we have one of the disjuncts. And the original sort of conceptual idea of the implication was that, to say, if I have a proof of the antecedent, then I can obtain a proof of the consequent. You can think of that more generally as saying something like something more to do with resources. So if I have a resource phi, then I can obtain a resource psi. For example, if we want to use it for something about reasoning, about actions, if I have a key, then I can access the building. And there are cryptography frame semantics for intrusionistic logic. Here we want to insist that the set of worlds of any atomic position is down and closed. And then the semantics of the implication will be that the implication only holds if at all the worlds below the world we're evaluating at, the classical implication condition. And then intrusionistic linear temporal logic is just combining these two formalisms. So we want to use the language of linear temporal logic that I presented, but we want the modality-free fragment of it to be either intrusionistic logic or some logic between intrusionistic logic and classical logic. So actually, usually we'll try and arrange so that the conditions for evaluating the modalities work exactly as they would classically. So these are the classical definitions that I mentioned before. And also to mention that there are also topological semantics for intrusionistic linear temporal logic. And we have some results about a particular intermediate logic, Gödel-Dummett logic, which is the logic of the class of linearly ordered cryptography frames, or alternatively, a disjoint connection of linearly ordered frames. So here are those results. So we have a complexity result about the validities of linear temporal logic for these frames, and we have an axiomatization. And more recently, we also have an axiomatization of the validities of intrusionistic linear temporal logic. There are decisions you need to make about exactly what frames you're using, but for one of those, one of the possible choices, we have that result. And the methods that we use, often these results are proved using the finite model property, but for the Gödel-Dummett logics that I mentioned, we don't have the finite model property, so we can't use that. But we use something called quasi-models and show that we have a finite quasi-model property. And the axiomatization result, you first try to produce a canonical model. It doesn't quite work, but then if you take a further quotient to the canonical model, you obtain one of these quasi-models. And open problems are, similarly, other results for other intermediate logics, results for topological semantics, or maybe change linear temporal logic to a branching time temporal logic, which there are also examples of in computer science. I'm thinking particularly of computation tree logic. Okay, topic 3, algebras of partial functions. This is something I've worked on for a long time, back to my PhD. I'm currently working on it with these two people. So the idea is that we want to reason about partial functions, collections of partial functions, combining partial functions in various ways. So we treat a collection of partial functions as an algebraic structure if it's closed under certain operations that we're interested in. And these are some of the operations we could use for partial functions. You can compose them, you can take their intersection, you can have various other operations that are encoding information about the domain of the function or the range of the function. You can do more complicated things like try to take a union of two functions, and then but in order to make sure that's still a function, you'll have to use some sort of definition. Here's one choice of a definition. So the preferential union of f and g takes the value of f if possible. Otherwise, it tries to take the value of g. And if neither of them are defined, then it's undefined. Here's a more complicated operation. And then so we turn collections of partial functions into algebraic structures, and then we want to study these classes of algebras from a logical and computational perspective. Why? Well, there's a long history of this being done for binary relations. They've been extensively studied. So I think, why not functions? Functions are very fundamental to mathematics and also useful in computer science. What's good is that the results for partial functions are almost always more favorable than the results we obtained for binary relations. I think you'll see that on this following slide. And the practical application is that if you think of each partial function as the action of a computer program changing the state from the input state to the output state, then we could use this formalism for formal verification of programming. So here's a comparison of binary relations and partial functions. So the classes that we obtain in the case of binary relations, often these classes are not finitely axiomatizable, but for partial functions, I think in almost every case, the class is finitely axiomatizable, and also often by equations. If we want to decide if an equation is true, then for binary relations, this problem is usually undecidable. But for partial functions, it is usually decidable, even in quite low complexity classes. Another property that we're interested in, finite representation property, again, is a difference. If I'm given a finite algebra that I don't necessarily know is an algebra of binary relations, can I decide if it is isomorphic to an algebra of binary relations? That's this problem, which is undecidable in general. But if I ask the same question about partial functions, then usually the answer is that it's decidable. And we study also some more specific classes that I won't discuss, called the completely representable classes of algebras. And again, we see there's a difference that partial functions are more well behaved. The methods. So this is the method for proving an axiomatization is correct, is that we want to take an algebra that we assume satisfies, validates the axioms, and we want to show that in that case it is indeed isomorphic to one of these concrete algebras of partial functions. And so we have this problem of turning this algebra that satisfies axioms into the concrete algebra, and we do this by combining two very well known and fundamental ideas. One from logic, Stone's representation of Boolean algebras by sets of ultrafilters, and one that I think everyone encounters in their first year studying mathematics, Cayley's representation of groups as actions of the group on itself. So this is a way of representing certain algebraic structures as sets. This is a way of representing certain algebraic structures as bijections in this case. And we sort of combine these two ideas. And the open problems we have in this area, well, we have some of the basic questions for some combinations of operations. The basic questions may still be open. I mentioned axiomatization, complexity of equational theories, for example. We want to maybe do this more. At the moment, we're doing this for individual collections of operations at a time. Maybe it would be better to have a sort of meta theorem that could treat whole families of signatures. Duality theory is a method of turning collections of algebras into usually collections of topological spaces, and that's been useful in logic, and we want to develop some of these dualities in this context, and maybe even go a bit further. Some of the dualities, for example, stone duality has been enriched in a way that can tell you things about formal languages, regular languages, for example. Maybe we could do a similar sort of thing. So you may know that regular languages are related to automata. These partial functions may be related in an analogous way to finite state transducers, which are computational machines that you give them a word in and they give you a word out. So word-to-word partial functions. And maybe we could use some of these extended dualities to tell us, or to give us an algebraic way of looking at and analyzing finite state transducers to answer some questions there. And that's the end of my talk.
Yeah, thank you very much. Other questions? Yeah.
Second part about deterministic
Yeah.
linear temporal logic. So I think in the beginning you have been hinting at this kind of computability interpretation of this logic. So in terms of like that you could deterministically reason about programs. I think it's somewhere in the beginning of this.
I don't know if I read it here, but yes.
But do you have any sort of kind of formal interpretation of this, or some sort of realizability style semantics for this deterministic temporal logic, or something along these lines?
I don't think that exists, no.
Well, because it did be quite natural. You did want to somehow justify that. Okay, but I think it's conceptually it's not very obvious what should be like a deterministically appropriate way of reasoning about systems evolving in time, right? And then we have some particular more.
Yeah, I mean, several people have proposed ways of applying this that they think would be useful. Firstly, I've never really looked at the details in that much detail. But what I have seen, I wouldn't necessarily immediately think that they're onto something good, but
Okay.
I mean, I don't know.
Yeah, further questions? Other questions from the online participants? That's not the case, then I will stop the recording.